The age of our current universe is 13.7 billion years old. The size of the universe is 93 billion light years. That seems to be a contradiction because we know that the speed of light is such and such. How could the universe be larger than a radius of 13.7 billion light years? Well, that 13.7 billion light years that we're looking back on to see the Big Bang radiation has been stretched over that time period, just the same way the light has been redshifted.
The Rational View is a weekly series hosted by me, Dr. Alan Scott, providing a rational, evidence-based perspective addressing important societal issues. Hello and welcome to The Rational View. I'm your host, Dr. Al Scott. For this episode, I'm going to talk about observational cosmology. Now, this is a pre-recorded talk from YouTube that I made in 2015 to the Ottawa Chapter of the Royal Astronomical Society of Canada. And this presentation was awarded their Best Presentation of the Year award. So I hope you enjoy it. I am going to be taking a little bit of time off on vacation, so I thought I would give you some interesting content to listen to. Although it's not new content, I hope you enjoy it. Thank you for listening.
I wanted to give a talk tonight to go over the most recent advances in modern cosmology, but I thought to get there we should start at the beginning and go back and really look at why we think what we do about the history of the universe and our place in it. We're very lucky right now that we live in a golden age of science. For the first time ever, I think over the countless millennia that our ancestors stared up at the night sky in awe and wonder and postulated a solid firmament populated by mythical creatures, basic scientific research has now given us an accurate picture of the history of the universe and our place in it. And I want to go over some of the measurements and some of the observations that have led us to this place, and what we know and what we don't know, which is also quite interesting, I think. So let's start at ancient cosmology and the ideas from long ago. We know that the biblical authors pictured the earth as a flat disk floating in water, with the heavens above and the underworld below. The firmament for them was a solid inverted bowl above the earth, colored blue by the cosmic ocean. It kept the waters above from flooding the earth below. A glow within this firmament was responsible for dividing day and night. Lights within the firmament were the stars, and responsible for signs and portents. The ancient Greeks as well had their own system of a firmament. They had a series of crystal spheres, each one associated with one of the moving heavenly bodies. These spheres started with the earth in the center, the imperfect, and moved outwards to the perfect, each layer becoming more heavenly. Each of these heavens, the 7 planetary heavens, the moon, the Mercury, Venus, the sun, Mars, Jupiter, Saturn, they moved independently, and they seemed to move randomly across the sky. They did not always move smoothly. Sometimes the planets appear to go backwards through the sky, as if at the whim of a deity. And that is all that they could tell without the insights of Kepler and Newton to guide them. These nested crystal spheres, at the outside of which there was the heavens. In Latin, this is the empyrean heaven, dwelling of God and the elected ones. Out in the most perfect, where beyond the realm of the fixed stars, which was this sphere here, where nothing moved, everything was perfect and unmoving. Moving on, Renaissance cosmology changed that picture. Copernicus in the mid-1500s moved the Earth from the center out to a supporting role, third from the sun as we know it now. He stuck with spheres because those were the perfect things, and he could not think of any reason why not to use perfect spheres. And again, he maintained that the stars were on a crystal firmament. This model was an improvement on the previous model. It explained the difference as to why some of the planets appeared to move retrograde in their orbits. Because the Earth is no longer at the center, relative velocities make some of them appear to go backwards across the sky. It explained the difference between the inferior and the superior planets, why Mercury and Venus were always close to the sun, and Saturn and Jupiter and Mars were able to go across the sky. That's an interesting symbol. That should be a degree. It predicted the positions to less than 2 degrees, which is roughly as good as the Ptolemaic model. The Ptolemaic model, the Greeks have been adding epicycles over the years to try to account for the imperfections in the spheres and the mismatch between them and the actual observations. So it wasn't really an improvement in terms of the positioning over the other models. There were also some problems with the model. It required the Earth to move. And people obviously realized that the Earth wasn't moving. We weren't flying off of it, and doesn't feel like we're rotating. So there was a problem. There was no model to predict why this could actually be the case. It was an interesting way to predict other things. And also there's been no stellar parallax. Stellar parallax is the way that stars appear to move, nearby stars would appear to move relative to background, more distant stars as the Earth traverses its orbit, just because of the same sort of thing that you see as you're driving along the road. Close by objects move with respect to faraway objects as we move along. That's never been observed up to this point in the mid-1500s. The stars are maybe infinitely far away. People did not know. Renaissance cosmology continued with the insights of Kepler. His Astronomical nova in 1609 derived universal laws of planetary motion. And this was based on observation. The observations of Tycho Brahe, his mentor, painstaking observations of the position of Mars over 20 years showed irreconcilable errors with a spherical or a circular orbit. This great data allowed Kepler to move to an elliptical model where the sun was at one focus of the ellipse. The orbits that the planets traced out followed mathematical laws along these ellipses, tracing out equal areas in equal times. But nobody knew why. There was still no physics to explain why this was so. We still needed angels to push the planets along in their orbits. And still no stellar parallax had been observed at this point. The insight was one of Newton's in his Principia in 1687, where he realized and put down on paper the theory of universal gravitation that explained Kepler's laws in a simple equation that showed that the gravity that drops apples to the Earth is the same force that makes the planets move in their orbits. And he derived this universal law of gravitation, and then suddenly we have an explanation for why the planets are moving in these orbits and following these laws. Following this, Edmund Halley in 1718 was measuring the positions of stars, of bright stars. Sirius, Arcturus, and Aldebaran apparently had moved more than half a degree from what Hipparchus had written down more than 1850 years before in his Greek catalogue of the bright stars. And this is starting to lead us to the idea that maybe the stars are actually moving and not fixed. Following this, we go to the modern theory of cosmology. Maxwell, in 1861, came up with the modern theory of light. And Maxwell's equations tell us from magnetism and electricity how light travels as a wave through space with a fixed speed. And this is all well and good, but it is odd that light would have a fixed speed. In the Newtonian world, things move at different speeds depending on the observer. But Maxwell's laws didn't have anything about the observer in them. The speed of light came out as a constant. And so Einstein pushed forward on this with a theory of relativity, the modern theory of gravity. And he basically started with the idea that physics should be the same no matter how fast you move. And so what this means is that no matter how fast you move, the speed of light that you measure is the same. And for this to happen, what it means is that time depends on how fast you're moving. Your experience of time depends on how fast you're moving. Your experience of space depends on how fast you're moving. And different people will see different events happening at different times. One person may see two events that look simultaneous to him, but if someone is moving in a fast direction along the line between those two events, they will see one happen before the other. Einstein's theory of relativity broke down simultaneity. Simultaneous events no longer exist in relativity. You have to specify your speed before you can say anything about past, present, and future. Out of this, he also showed that he united inertial and gravitational mass. Basically, Newton's laws said that masses pull on each other. Einstein said that masses curve the fabric of space and time around them so that objects move in a straight line in space, even though they appear to move in circles. And this is a really weird realization that time and space aren't linear fixed grids like Newton had thought. The interesting thing was that this could be tested. The predictions of Einstein's theory could be tested. And going through this curvature of space, the curvature of space by the sun predicts something different than Newtonian physics at the fine level of detail. In fact, there'd always been a problem with the orbit of Mercury. The way it precesses was not explainable in Newtonian physics, but relativity explained it. Relativity also had several other predictions that were subsequently verified. Einstein predicted that gravitational bending of light paths, light made up of massless photons, would not bend in Newtonian physics. But because space itself is bending, the straight line of the photon bends as it passes close to the sun. And this was verified by measuring the positions of stars during a solar eclipse. As they moved close to the sun, their position changed by fractions of an arc second that were exactly predicted by relativity. Further verification has happened over the course of the 20th century. Redshift of light moving from out of a gravitational well, the frequency becomes a little bit redder. This was verified around 1960 and onwards in several experiments. Time dilation, the fact that time is experienced differently by different observers, was verified by atomic clocks flying in jetliners in 1972. They predicted gravitational lensing by massive galaxy groups. It was verified by telescope observations in 1979. Predict orbital decay through the emission of gravitational waves. This was verified by the observation of binary pulsars in 1994. Goes on and on. It's an amazing insight, this theory of modern gravity. And this underlies our modern cosmology. And the math behind it we can use to make predictions about the history of the universe. One thing we notice from this is that the shape of the universe is not necessarily what we call Euclidean. We are used to measuring triangles in the local area and adding up the angles to 180 degrees. And one analogy to this is the surface of the Earth. You can see a triangle that you would make on the size of a city. The angles will add up to about 180 degrees. But as you go to larger areas on the curved surface of the Earth, you can see that this triangle adds up to 230 degrees, even though it is a perfect triangle. And the reason is that the underlying geometry of the system in which the triangle is inscribed is curved. It's not a flat Euclidean space. And what Einstein's theory said is that the three-dimensional space that we live in is curved in just this way by nearby masses. So we can build triangles here on Earth and measure them in 3 dimensions, and they are 180 degrees. But if we build larger and larger triangles and there's enough mass nearby, the angles will add up to more than 180 degrees. And this just shows different types of geometries here that one might expect. This is a 2-dimensional representation of a 3-dimensional space. And so Einstein's equations say that there's a critical density. And if the large-scale density of the universe is equal to this critical density, then the geometry of our universe is flat like a sheet. And no matter how large a triangle is, it will always add up to 180 degrees. But if the density is just a little bit more, then on large scales, we will actually have a closed geometry, a closed universe. The universe will be finite but unbounded. You will be able to move in any one direction, and then you'll come back to your own originating place. and eventually everything in the universe will collapse in on itself. Or if the density is a little bit less than this, then parallel lines you draw will eventually diverge, and the universe will expand away forever and accelerate away, in fact. This critical density we now think is on the order of 5 hydrogen atoms per cubic meter. Seems very low. Most of space is empty, though. And we think from our current observations that the universe is very close to flat. Now, of course, this is on the very largest scales. There's obviously bumps and hollows where planets and black holes and things are, but over the size of galactic superclusters and intergalactic superclusters, if you average all that out, in general, we think the universe is pretty flat. And in fact, even if the universe is flat, it doesn't mean that the universe is infinite. Even in this case here, this is a simple topology. What this means is that there's no connections. You don't wrap around the screen, basically. But Einstein's theory doesn't say anything about how the universe is connected on large scales. It could be that even if the universe is flat, the topology could be that of a torus or something that would allow you to come back and as if you were living in a hall of mirrors and you could see the same galaxies over and over again as you look around the universe. We don't really know if that's the case yet. People are looking for that signature in the distribution of galaxies and have not found it yet. So how big is the universe? Well, historically speaking, up to about 500 BC, the world was a small patch around the land, a small patch of land around your village. Around the time of 500 BC, though, the Greeks realized that shadows change with latitude. And what this means is that we're living on the surface of a spherical Earth. This was known in 500 BC by the Greeks. Around 300 BC, Aristarchus of Samos suggested that maybe the stars are other distant suns. Then, soon after that, there was a problem. The Romans came, there was Dark Ages. Not much happened for a long time in the science. In 1584, Giordano Bruno suggested that the stars might be other distant suns. He was burned at the stake by the church. Although people were still curious, in the mid-1600s, Christian Huygens continued to scratch away at this. He said, what if Sirius was as bright as the sun? We know now that Sirius is actually much brighter than the sun. He said, it must be billions of miles away because of its current apparent brightness. Billions of miles away. In 1838, Friedrich Bessel was the first person to ever measure parallax of a star. This is the 61 Cygni. The parallax he was able to measure was 0.314 arcseconds, a very small change from one side of Earth's orbit to the other. And the distance this signified for one of the nearest stars, 61 trillion miles. Mind-boggling. Continuing on with the growing universe, in 1915, Harlow Shapley used Cepheid variables. These are giant stars that oscillate in a fixed period. And we know, and they knew back then, that the period of these stars, by measuring, you can tell by the parallax of nearby ones, the period of the stars depends on their intrinsic intensity. So we have a relationship. If we know the period, we know how intrinsically bright the star is. So we can measure the period and its apparent brightness, and we know how far away it is. So he used these Cepheid variables throughout the Milky Way to measure the Milky Way. And we know now that we're about 30,000 light years from the center of the Milky Way, and the Milky Way is, twice that big at least. Following this, there was a controversy, the famous Shapley-Curtis debate in 1920. At that point, the Milky Way was thought to be the entire universe, just our galaxy. But there were these intriguing little spiral nebula that people keep seeing, and they seem to have a really significant number of novae in them, more than you would expect in a small nebula. And people started to think, maybe these are other universes, another island universes. Several people, though, were a little bit worried about that. It pushed people beyond their comfort level to realize how drastically far away and isolated these things might be. They actually were able to use in 1924 Cepheid variables in the Andromeda Nebulae to answer the question, and finally, that these spiral nebulae were other island universes. The nearest one to us, the nearest major one, the Andromeda Galaxy, is 2.5 million light years away. This was how the universe grew. Following on, we now know because of the finite speed of light that distance equals age. The further back we look with our telescopes, the further back in time we are looking. So we actually can look at, in our nearby area, normal looking galaxies that look similar to the Milky Way. And as we look back further, we've taken a couple ultra deep pictures with the Hubble Space Telescope looking at what we think is the evolution of galaxies over time from simpler to more complex. Einstein's model, of course, tells us that the universe is likely to evolve. If it did not, it would probably collapse back in on itself in a big black hole. So looking back in time, we can learn something about the history of our universe. And in fact, there is evidence that emerged in the early 20th century for something that we call the Big Bang. A couple of people, Vesto Slipher first in 1912 and Edwin Hubble later in the 1920s, took spectra of nearby and distant galaxies, and they found that there seemed to be a scaling in what's called redshift. So here we see spectra of a star in our galaxy, a nearby galaxy, and two what look like smaller galaxies angularly on the sky. And if you spread out their light, you have this fingerprint pattern of mainly hydrogen absorption lines. Hydrogen gas is absorbing the light from the background stars. And that pattern shifts to the red. And what we found is that for the distant and even more distant galaxies, they were always shifted to the red, and more red the further away they appeared. And this is what they called the Hubble Law. It looks like, and we know from the theories of light, that light shifts. The wavelength of light shifts as an object moves away from us, like the Doppler signal in, say, a train's whistle shifts as the train's coming towards you. It's high in frequency. If it's going away from you, it goes lower in frequency. Light does the same thing. What this could indicate is that faraway galaxies are moving away from us very quickly. And so it appears the farther away a galaxy is, the faster it's moving away from us, shifting its light to the red. Well, what does this mean? Did we make some sort of cosmic mistake and all the galaxies are running away from us? Well, no. We can actually come up with an idea that explains this. In 1927, in fact, the Belgian priest Georges Lemaitre was the first to propose that the universe began with the explosion of a primeval atom where all matter and energy was contained. His idea was that this atom explodes into a pre-existing infinite space. We now know that that's not quite correct. What we now know is that all the matter and energy in the universe was crammed into a dense place, including the space. And what happened was that the space itself expanded. Every portion of space expanded from a primordial fireball and then began cooling over time. An analogy is a raisin bread. The raisins are galaxies, the bread is the space between. As you bake the bread, the raisins move farther apart, and the further the raisin is to start, the faster it moves away from you. This same picture is seen by every raisin in the bread. So we aren't in the center of the Big Bang necessarily. What we're in is an expanding raisin bread of galaxies, and space itself is expanding. Another more intuitive, something that may be more intuitive for some people, is to think that none of the galaxies are moving and everybody here is just shrinking. And in fact, it's completely analogous, because all we can do is measure the ratio between our rulers and the spaces between galaxies. And we know that either we're shrinking or they're moving away fast. So how old is the universe? Well, we can measure the Hubble flow, or the speed, redshift of a galaxy with distance in various different models. You can look at standard candles like supernovae, which we know the intrinsic brightness is roughly the same, and we can measure the redshift versus the brightness of these things, and we plot this curve. This is the Hubble curve. The Hubble Space Telescope key project. Hubble Space Telescope was defined to measure this expansion history of the universe, and we know now that the Hubble constant is 67.8 kilometers per second per megaparsec, and if we integrate that back to the point where everything was in the same place, it's 13.7 billion years. So this is the first time in the history of our race that we actually know how old the universe is and what our place in it is. Several independent methods give roughly consistent numbers with less precision than the models that we use. This brings up a problem, though. We call it the flatness oldness problem. It's not really a problem, it's really a good thing. For some reason, the universe seems to be perfectly balanced on a knife edge to be flat. We know that if it had a little bit more density, even 1 nanosecond after the Big Bang, in fact, to the 25th decimal point, the density is very important. If it was 2 points in 25 figures less or more, it would have recollapsed by now in another big crunch. If it was a few points less, it would be accelerating apart just due to the gravity right now. So this is what we call an interesting coincidence that we don't really have a good explanation for. And it's one of those things, some people could think it's an anthropic principle. Maybe these other universes aren't amenable to life. Human life wouldn't be there to observe them, so therefore, because it's kind of a circular argument, other people postulate a special god of the gaps who likes to balance mass energy. Or there could be some new physics. One of the really interesting things, though, that came out of Big Bang theory is Big Bang cosmic nucleosynthesis. If we run everything backward, this was first posited by a famous paper by Alpha, Betha, and Gamma, which, alpha, beta, gamma, it's very funny. Betha wasn't actually involved, but they brought him in just because of the title. In 1948, we knew a lot about nuclear physics. We knew the cross sections and the rates of reaction at temperature, and we could actually predict, based on thermodynamics and nuclear physics, what might have happened in those first few minutes as the Big Bang expanded out. And we've run the models, we know the cross sections. What should happen is that we should have 75% protons, 25% helium-4, traces of deuterium, lithium, and beryllium in the primordial universe. And in fact, everywhere we look, the ratio of hydrogen in the universe to helium is 3-to-1, just like nuclear physics predicts. This is one of the key stones of evidence on the Big Bang, that our understanding of nuclear physics in the first few minutes, up to 20 minutes after the Big Bang, predicts the ratio of hydrogen to helium in the universe today. And the density of deuterium and other traces tells us a little bit about the amount of matter, the density of matter that was in the universe in these early times. So this is really an amazing prediction. And from this we know that from the deuterium concentration of the current universe, it's a little bit low actually. We know that the density of matter that would be needed to produce the deuterium that's in the universe, and it's actually only 20% of what we would need to make a flat universe. By Einstein's equations, the universe should be expanding rapidly away. And this is when the postulation of dark matter came in. This is one evidence for dark matter, and there are other evidence that support the existence of dark matter. But dark matter is a non-nuclear matter, some sort of exotic thing that provides gravity and density, but does not actually participate in these reactions. So that's an interesting side effect. After nucleosynthesis, we have everywhere in the universe a hot primordial plasma, populated mainly by high-energy photons, like what we find inside a core of a star. And as the universe continues to expand, it continues to cool. The temperature drops. It's like moving from the core of a star out towards the surface, but we're not moving in space, we're moving in time. As the universe cools down to 10,000 Kelvin, the protons start to recombine with electrons. However, we have to wait until it cools to about 3,000 Kelvin before neutral hydrogen can form and not be immediately reionized by the photon soup. At that point, photons decouple from matter and are free to pass through the universe. We change from this foggy plasma to a transparent universe at this temperature. So if we could postulate an observer in the early universe, you would find yourself in a red fog that slowly dissipates over about 100,000 years. The sky in all directions would be red hot, as though you're in the center of a blast oven, and would appear to cool slowly to black over millions of years. As the universe expands and the wavelength of the cosmic background echo of the Big Bang shifts out of the visible spectrum. In fact, Alpha, Beta, and Gamma predicted that we would still be able to see the afterglow of this explosion if we looked far enough away. It would be shifted into the microwave, and it would appear like a black body between around 5 to 50 Kelvin is what they thought. In 1964, a couple guys in Bell Labs made the most sensitive radio dish ever built. There shouldn't have been noise, but wherever they pointed it, they found a microwave hiss. They had actually discovered this afterglow. They got a Nobel Prize for this discovery. This microwave background is coming from all directions. It's 3 degrees Kelvin. It's the temperature of the universe from this fading blast furnace. It's actually almost a perfect black body, as you can see. We can tell very precisely what the temperature is. If our theories are correct, we are looking back in time 13.7 billion years to the afterglow of the primordial fireball, a universe-spanning star that was aged about 380,000 years when it last emitted this light. Of course, a perfect featureless background would not be consistent with our understanding of cosmic history. For galaxies and clusters to form, there must have been some hot spots and some cool spots. These would serve as condensation cores for gravity to begin accumulating matter into galaxies and galaxy groups. These would be also formed as sound waves in the plasma, ringing from the Big Bang itself. To see these, we would have to send up a satellite, so we did. The Cosmic Background Explorer was launched in 1992, and its job was to find the echoes of the Big Bang and map them. And this is the all-sky map in a color scale of about 0 to 4 degrees. And you can see that it's a very featureless 2.728 Kelvin. But if we subtract the mean black body off of this, this is what we see. There's a distortion, and it's about 3.3 millikelvin, and it's a dipole. And this is expected. This represents our motion with respect to that last scattering surface. This is a Doppler shift. We are moving towards this area of the sky of the average velocity of the universe back then, and away from that area of the sky. And so if we subtract this dipole off, this is what we see. We see thermal radiation from the Milky Way galaxy in a big red band. And if we subtract off the thermal radiation from the Milky Way, this is what we are left with. If we are right, this is a map of a spherical shell through the universe as it would have appeared 13.3 billion years ago. At the time the light was emitted, this map would have encompassed a sphere of 42 million light years in radius. At the present time, I use scare quotes around present because of relativity, the fluctuations we are seeing in this map would represent galaxy clusters that have now expanded away from us and are now 46 billion light years away from us. This is as far back as we can see with telescopes. We sent up other satellites to learn more about this background radiation. In 2008, we launched the Wilkinson Microwave Anisotropy Probe to look at this with higher resolution to map the size of the oscillations that eventually form galaxies. Astronomers are looking for patterns in the background radiation that might tell us about cosmic geometry. If we correlate the angular size of the ripples with the size of the galaxy clusters and superclusters, based on our models of cosmic expansion histories, we can find remarkable agreement. And in fact, 2014, the WMAP team released its analysis of the microwave background data that shows that the observable universe at the scale of this map is flat within 0.4%. So we're very Euclidean over largest scales. This was followed by the Planck satellite in 2013. Planck was set up to measure polarization in this background. And in fact, one of our our news item last month discussed the polarization of the background. Planck is refining the map, and it's hoping to find fingerprints from cosmic inflation on these ripples. And the ripples, in fact, can be correlated with angular scale. And there's what you get on the right is a power spectrum of different angular scales and the ripples of this background radiation. The statistical distribution of the size and density of the hotspots tells us something about how sound waves traveled through the plasma in the early universe. It tells us about the density and the viscosity of the universe at that time. And it strongly constrains the set of initial parameters that resulted in our universe today. Cosmic inflation is consistent with the pattern shown here. In fact, the red line is our model, the dots are the observations. Many more exotic theories have been ruled out by this. So just to get to a point where I can recap a little bit about our understanding of galactic evolution and what we know from looking back in time with our telescopes. This is the Hubble Ultra Deep Field. And more distant galaxies are redshifted, looking orange, and then the most distant ones are just single pixel red spots. This type of image suggests that there are more irregular dwarf galaxies at deeper redshifts. And this suggests that older galaxies were smaller. I mean younger galaxies. Galaxies that are further away in time from us were smaller and in the process of coalescing into larger modern galaxies. There also appears to be orders of magnitude more star formation going on in these older galaxies than there is in the current universe. We've found quasars in the far distant universe, very highly redshifted, extremely bright objects, which we think are gigantic black holes at the cores of early galaxies, accreting mass and beaming radiation out into the universe. These are mostly seen in the distant universe where there's still a lot of gas coalescing into stars. The spectra of these quasars, though, show superimposed absorption lines from light passing through interstellar clouds of neutral hydrogen, also at high redshift. We now expect that a few 100 million years after the electrons and protons combined to neutral hydrogen, that the first stars were formed. And these stars started spewing out ultraviolet radiation and reionized these neutral clouds so that they no longer were able to absorb the quasar light. And that's consistent with what we see in what we call the Lyman alpha forest in these spectrums. Globular clusters, even in our galaxy, appear to be undisrupted remnants of an earlier time. They consist mostly of old red stars, these globular clusters. In fact, the oldest known clusters have metal-poor stars, suggesting that the universe has become enriched in the heavier elements from supernovae over the years since they formed the first stars. Theories of stellar evolution, based on our knowledge of nuclear physics, show that most of the ages of the clusters are younger than what we think the universe is. There are no anomalous clusters out there that are clearly older than our estimated age of the universe. So what's this dark matter stuff that I mentioned before? This came about mainly in the 1970s. We know that the geometry of the universe is close to flat, but the density of normal matter, the matter that we understand, is nowhere near what is needed to make it flat. So other things that predict the existence of dark matter, that galaxies actually rotate faster than they're expected to rotate. We can measure the rotation rate of galaxies by looking at the differential Doppler shift in an emission line across them, like this map here. The red is moving towards us, the blue is moving away from us. We can measure the rate of galaxy rotation by taking these spectra. And we would expect, based on the light from the stars, that, and Newton's theory of gravity, that the rotation rate should slow down as you get towards the outside. But they don't slow down. They rotate as though they are solid bodies. And what this means is that if our theory of gravity is correct, there should be a lot more mass extending a lot further out the galaxy than what we see in just the normal matter. And this is what we call dark matter. Another recent surprise is dark energy. Nobody was expecting this. Astronomers were measuring standard candles. They were taking censuses of distant supernovae, and they wanted to measure their brightness versus their distance, and they expected that the universal expansion from the Big Bang would be slowing down due to gravity. We expect in a flat universe that things should slow down and then eventually peter out in its expansion. What we found actually was the reverse. Typical magnitudes of these supernovae are about minus 19.3 in absolute magnitude with little variation. We were able to find this expansion and nobody knew what it was. Nobody knew why it was there. And so they postulated, they gave it a name, and that made them more comfortable. Dark energy. So, based on our best models, we now believe that matter is 30% of the mass energy content of the current universe, and dark energy is 70% of the current density. And this dark energy seems to be accelerating the cosmic expansion rather than decelerating it. So that was a surprise, and it led to a Nobel Prize as well. Now I'm just going to touch on inflation. This is also something that came out of the 1970s, and it was introduced to try to solve a few problems in our understanding. One is that coincidence of the flatness oldness that I told you about before. Inflation is when they had the Big Bang and suddenly the universe went through some sort of a quantum field transition and everything expanded much faster than the speed of light. And what this also explains is why the universe looks the same temperature in both directions. We don't understand why the universe is the same temperature in all directions. A priori, you could just say that it's that way, but that's not a good explanation. So why is it the same in both directions? Well, they said that they were initially in contact and they were stretched out by inflation. That's the layman's version of it. But what we think we know now is that inflation is running into problems. Inflation actually has to be very fine-tuned to produce the sort of universe that we find as well. So it doesn't really solve the problems, it just pushes them back a level. It gets rid of the monopole problem. Many of our theories suggest that the universe should be filled with extremely heavy magnetic monopoles, and they're not there. So inflation suggests that they were initially there, but then they were inflated away. So why aren't hypothetical particles seen? Because of inflation. It also predicts a unique pattern of polarization in the background radiation, and this is what the Planck mission is looking for. And there was a preliminary announcement that it had been found last year that was promptly retracted because the data was wrong. But they're continuing to analyze the data and refine it. It's not going to be a bright signal, they don't think, but they may find it. We have to reserve judgment until the data comes in, but interesting times ahead. So I'm getting to the summary part. What do our current models tell us about the current universe? The age of our current universe is 13.7 billion years old. The size of the universe is 93 billion light years. That seems to be a contradiction because we know that the speed of light is such and such. How could the universe be larger than a radius of 13.7 billion light years? Well, that 13.7 billion light years that we're looking back on to see the Big Bang radiation has been stretched over that time period, just the same way the light has been redshifted. So, as I said, those points on the map of the background radiation are now 46 billion light years away from us in what we call a co-moving frame. If we were sitting there and they are expanding away in the same Hubble flow that we are from the Big Bang, it's much larger. Because it's the metric defining distance that is changing rather than objects moving in space, this expansion that we see is not restricted by the speed of light, of course. The expansion of space, the stretching of space, can exceed the speed of light if it wants to. There's nothing in Einstein's theory that constrains the stretching rate of space. Einstein's theory deals with the movement of objects through space, physical objects moving through space. If the metric that defines the distance between objects is expanding, it can expand any way it wants. So that's an interesting way to think of it. But basically what we know now is that the universe is 4.6% atoms, 23% something we don't know, and 72% something we don't know. But I always say that the road to knowledge is admitting what you don't know. So now we know what we don't know. And it's an interesting time because now we can find out what these things are. And people are are planning the next generation of spacecraft that are going to map the three-dimensional structure of galaxies to even better precision in the distant universe, so we can learn more about what this dark energy is and what the real expansion history of the universe has been. What's the fate of the universe? Well, we don't really know, because we don't know what dark energy is going to do. Naively, we would think that we're kind of a flat universe, and so what's going to happen is the big freeze. Without dark matter or dark energy, things would just expand forever, cool down, and freeze. The universe continues to expand asymptotically forever. After 100 trillion years, all the stars burn down to cooling white dwarfs, neutron stars, and black holes. After 10 to the 37 years, all that is left are a smattering of black holes slowly evaporating through Hawking radiation. The universe then becomes a uniformly warm soup after a few trillion years with no free energy. After a Google of years, only the waste products from these processes remain, mostly photons of colossal wavelength, neutrinos, electrons, and positrons. For all intents and purposes, the universe would have dissipated. The Big Rip, of course, accelerates this process immensely. If dark energy continues to dominate the universe, and we don't know what it's going to do, it might, it could strengthen until it overcomes all of the binding forces that hold us together, rip all the particles in the universe out to unimaginable distances, and leave behind a void. The Big Crunch is the opposite, of course. The acceleration of the universe could end by gravity. Everything ends up coming together for a cozy homecoming. There are also corollaries of this theory called the Big Bounce, where it comes together and bounces out again and starts the whole process once again. Of course, as I say, there's a lot to learn yet. There have been some interesting controversial observations, and I'll just touch on them briefly before I finish here. Other people suggest an ending in a vacuum transition brought about by one of these super colliders, which create another inflationary period or trigger it. Most physicists think that's pretty unlikely. It's not enough to stop doing it. So, summarizing the modern advances, for the first time in history, we have a cosmology based on observations rather than myth. We've mapped the three-dimensional structure of the local universe. We know the age of the universe to better than a few percent, and most things that we measure are in agreement with this. We appreciate for the first time the awesome vastness of the universe, billions of galaxies, each with billions of stars. And we've learned that there's still a lot we don't understand. And just as a teaser, I'm going to show you some of the tantalizing stuff from the new maps. The data that we have now of the cosmic background suggests there may be a north-south asymmetry. There seems to be, this has been highlighted a little bit here. And there's a cold spot over here. This could mean that we are seeing some weird topology, wraparound effects perhaps in the universe. Or it could be something that tells us about how the constants, the physical constants of the universe may be varying over cosmological distances. We don't know. This isn't. This is just speculation at this point, but it's interesting to think about. In fact, I've mentioned in the past about some other controversial observations. People have looked at quasars and they've found there's an asymmetry in the physical constants that govern the absorption lines in quasars, and it just happens to be 1 part in 10 to the 5th between the north and the south hemisphere. So perhaps there's something there, perhaps not. Interesting to follow along and see what comes out of the new measurements that we're making. Thank you.
If you're enjoying what you're hearing, please consider visiting my Patreon page and becoming a patron of this podcast at patron.podbean.com/TheRationalView.